Today I'm going to talk you through the new Threshold Simplex release with our example application, commonware bridge. So in front of us we got a terminal screen. We don't quite have any UIs cooked up yet, but maybe for future demos we can get that going. You can follow along on this demo on the commonware bridge docs. It has a step-by-step guide of how to do exactly what I'm about to show you. But I'll talk you through it here and provide some additional context that might help you actually figure out how to extend it or play around with it a bit more than what the example has going for it. So cool. All right. So the whole premise of Threshold Simplex is that at each view we generate both basically there's an embedded VRF that generates a beacon at each view for leader selection, and every consensus decision has a threshold signature over it. So if you have access to like the static public key that's associated with an instance of Threshold Simplex, you can verify anything that comes out of it just by having that hard-coded static public key and some certificate. So in that case, in this case, that certificate is a finalization result, which coincidentally is exactly what you would need to build a bridge. So to first get started, instead of doing a DKG or resharing, what you would typically do in production to instantiate a threshold shared secret, we instead have this dummy dealer that instead generates a shared secret and then the shares for each validator. So we'll first generate it for the first network. So this demo, there are two networks, both running independent consensus, both with a static public key. And then there's an indexer that sits between the networks that either network can query for finalization certificates from the other network. Now, in practice, you could replace this indexer with like a client wallet or whatever you want. But in this demo, it's all about trying to keep it simple and the focus on the interoperability between the consensus instances using threshold signatures and consensus security. So like I said, first we're going to create the threshold, basically the shared secret for the first network. So got a little compilation to do here. Love Rust. So you can see what we have here is basically a group polynomial over basically that serves as what we'll need to verify the partial signatures produced by each validator during signing. And then we have the static public key, which is just the constant term of this group polynomial, and then each share for the validators. So these shares are what will be used by each validator to actually generate a partial signature that could then be recovered to form a valid signature from this public key. So that's what we need for the first network. And then we'll do the same thing for the second network here. And so we do a lot to make these demos easy, so you shouldn't use these things in production, but we seed each of these so that they're reproducible. And then we also accept arguments for like participant public key seed generation, which is how we actually sort things in consensus to determine like the index for each participant, which is not this is the seed to generate a public key, and then we sort the public keys. So you can see like the index 0 is actually validator 6, which has a public key, which is the first one in this range when you sort them. So now that we have these generated shares that basically, if any, basically 2f plus 1 of them sign, they can generate a threshold signature that can be used to against this public key. We then now create basically ingest them into consensus, and we can get things moving. So there's 4 tabs here, so bear with me. But so the next thing we'll do is start up that indexer I talked about. So this indexer, what it's going to do is listen on port 3000. This is using commonware stream, which is basically a point-to-point encrypted transport that verifies on both sides the public key of basically the person you're dialing using the cryptographic public key, not some directly, rather than using like TLS or noise or something like that. So you can see here for the participants, participant 1 is actually this public key, participant 2 is this public key. So now you can, in hex, so you could probably see now how we actually sort them and why the ordering is a little different. And then we also provide it the public keys or the static public keys of each network so that it can verify the final, basically the finalization certificates, what we call succinct consensus certificates when they're uploaded. And then we provide the full list of participants that can connect to it because we don't want to store junk from different people. So in the next tab, we're going to start the 4 validators in network 1. So on the top left, I'll put, validator 1 here. Now, until 3 of these are started, we're going to be stuck in the first view because there isn't enough to actually generate a certificate to move forward. But you can see that it's running. So now we'll start the second one. It's going to connect to the first one, but still nothing's going to happen because we don't have 2f+1 online. But you'll see some like retry logic to see if it can get moving. And now once we start the third one, things will start moving here. And what's happening is when a proposal is generated, the proposal is actually posted to the indexer, and the other validators, before they actually vote to verify something, will fetch that from the indexer. Now, how blocks are actually produced is it basically does a 50-50 guess. And so half the time it puts random data into a block, and then half the time it fetches the latest finalization certificate from the other network, which we haven't started yet. So you'll see these like gaps where it doesn't do anything. And that's because there are no finalization certificates yet it could even include. And so it's moving, but you can kind of see there's missed slots. Well, you maybe can't see it in this video, but if you run it and look through the logs, you'll see that there's gaps. And so we'll start the 4th one here, and half the time now it should produce blocks. And the cool thing is we just did 100 views, but this node was able to sync right up to tip using basically Threshold Simplex's fast catch-up functionality. So we got one network going. You can see on the indexer, we're storing blocks, we're storing finalizations, they're sending them to the indexer, but it's only for one network, that first one. So now let's get things a little bit more interesting. We'll crank up the difficulty. So we'll now start nodes for the second network. So this is a separate group polynomial, a separate static public key, a separate shared secret. So we'll get things moving. Like our last time, they're going to be stuck until we get more online, and now more online. So now we have something special going on here where we're both producing random messages, but also occasionally including finality certificates from the other network. So because we have access to the static public key of the other network, anything that's actually included in the consensus here can be verified just with that key without actually following the consensus of the other network. And so we'll start 4 again here. And so, live demo. Just to show this wasn't pre-recorded here, we got a wrong argument here for the port number, so it was trying to bind to a duplicate port. So just goes to show you this is live demo. So you can see here it quickly joins, and then now we are cooking with gas. So all nodes are running on both networks. So 2 independent networks all running Threshold Simplex, and they're posting their results to the indexer to both do like block synchronization as well as to fetch finality certificates. Now in practice, you don't need an indexer. You can implement your own block broadcast within a network, but it shows we did this so that you could quickly see how you could actually pull these things together. But yeah, every other block, it's including a finality certificate, and in other blocks, it does a random message. And so yeah, if you had your own execution logic that wanted to reference some data that was signed over with a finality certificate, the network could do that and just use the threshold signatures directly for that. Now, yeah, the key here again is every finalization certificate is just a threshold signature of the static public key, and we can verify another network's outputs just by having that static public key, which is in our case 48 bytes here, and then every signature is 96 bytes, and then whatever the payload is. And so it's a really cool way to have many-to-many interoperability, and the way that we're utilizing it is to create these authenticated channels between consensus instances. But you could imagine using it to connect to a Ethereum smart contract or any other chain that can verify BLS signatures. So yeah, we're super excited for this and excited to see how you guys use it. Thanks.